Our world runs on electricity, a vital force that powers our modern lives. It energizes everything from our homes to our smartphones, making our daily routines possible. But have you ever stopped to think about how electricity actually gets to us? It's not as simple as flipping a switch. It's a fascinating journey that involves transforming electricity to different voltages, ensuring it can travel long distances and be used safely. You see, different electrical devices require different voltages to operate efficiently and safely. Your phone charger, for example, needs a much lower voltage than what comes out of your wall socket, which is why it has a built-in transformer. That's where transformers come in. These ingenious devices allow us to safely and efficiently change the voltage of electricity to meet our needs. Without transformers, we'd be stuck with a single, very high voltage that would be far too dangerous for everyday use, posing serious risks. Imagine trying to plug your phone charger directly into a power line. Not a good idea. Transformers make our electrical systems versatile and safe. Transformers are everywhere, even though you might not see them. They're hidden in plain sight, humming away quietly in power stations, on electricity poles, and even inside your electronic devices. At their core, transformers are remarkably simple devices. They consist of two coils of wire wrapped around a shared iron core. That's it. No moving parts, no complex electronics. Despite their simplicity, transformers are essential for our modern way of life. They allow us to generate electricity at power plants, transmit it over long distances, and then distribute it safely to our homes and businesses. The magic of transformers lies in a fundamental principle of physics called electromagnetic induction. This principle is the cornerstone of how transformers function and is essential in the transmission and distribution of electrical energy across vast distances. This principle, discovered by Michael Faraday in the 19th century, tells us that a changing magnetic field can induce an electric current in a nearby conductor. Faraday's groundbreaking experiments laid the foundation for modern electrical engineering and revolutionized the way we harness and utilize electrical power. Here's how it works in a transformer. When an alternating current, or AC, flows through the first coil, called the primary coil, it creates a changing magnetic field around the iron core. This magnetic field is dynamic and constantly fluctuates as the AC current changes direction. This changing magnetic field then induces an alternating current in the second coil, called the secondary coil. The amount of induced current depends on the number of turns in the secondary coil compared to the primary coil, allowing for voltage to be stepped up or down. The beauty of this process is that no direct electrical connection is needed between the two coils. This means that the energy transfer is highly efficient and can be done safely without physical contact. The energy is transferred wirelessly, so to speak, through the magnetic field. This wireless transfer of energy is what makes transformers so vital in our electrical infrastructure, enabling the efficient and reliable delivery of power to homes and industries. The number of turns of wire on each coil determines the voltage transformation. This is a fundamental principle in the operation of transformers, which are essential components in our electrical systems. If the secondary coil has more turns than the primary coil, the voltage will be stepped up, increasing the voltage. Conversely, if the secondary coil has fewer turns, the voltage will be stepped down, reducing the voltage. This relationship is expressed by a simple formula: V's over Vp equals N's over Np, which is crucial for understanding how transformers work. In this formula, V's represents the secondary voltage, Vp stands for the primary voltage, N's is the number of turns on the secondary coil, and Np is the number of turns on the primary coil. This equation helps engineers design transformers for specific applications. This ability to transform voltage is what makes transformers so useful. They are indispensable in both industrial and residential settings. We can generate electricity at a high voltage for efficient transmission over long distances, minimizing energy loss. Then we use transformers to step down the voltage to a safe level for our homes, ensuring that the electricity we use is both safe and reliable. Section 5. Energy efficiency, minimizing losses. No energy conversion process is perfectly efficient, and transformers are no exception. Some energy is inevitably lost as heat due to resistance in the wires and energy used to magnetize the iron core. However, transformers are remarkably efficient devices, with modern transformers typically exceeding 99% efficiency. This means that for every 100 units of energy put into a transformer, over 99 units of energy are outputted. Engineers are constantly working to improve transformer efficiency even further, using new materials and designs to minimize energy losses. Section 6. The challenges of long-distance transmission. Transmitting electricity over long distances presents a unique set of challenges. One of the biggest challenges is energy loss due to the resistance of the transmission lines. The longer the transmission line, the greater the resistance and the more energy is lost as heat. This is why electricity is typically transmitted at very high voltages, hundreds of thousands or even millions of volts. High voltage transmission reduces the current for a given amount of power, which in turn reduces energy losses. However, it also requires specialized equipment and safety precautions. Section 7. Solutions for efficient energy delivery. To minimize energy loss during long-distance transmission, engineers employ several strategies. One strategy is to use high-voltage direct current or HVDC transmission. Unlike AC, DC flows in only one direction, which reduces energy losses due to certain electrical effects. HVDC transmission is particularly well suited for long distances and underwater cables. Another strategy is to use superconducting materials for transmission lines. Superconductors have zero electrical resistance, meaning that no energy is lost as heat. While still under development, superconducting transmission lines hold great promise for the future of efficient energy delivery. Section 8. Transformers powering our world. Transformers are unsung heroes of our modern world, quietly and efficiently enabling the flow of electricity that powers our lives. From the power plants that generate electricity to the devices we use every day, transformers are essential components of the electrical grid. As we continue to demand more electricity and strive for a more sustainable future, the importance of transformers and efficient energy transmission will only continue to grow. These remarkable devices, based on the fundamental principles of physics, will continue to play a vital role in powering our world for generations to come.